This video is going to look at Joseph John Thomson's cathode-ray tube experiment. So in around 1897, J.J. Thomson was doing his cathode-ray tube experiment. The cathode-ray tube essentially consisted of two plates with charges. So one plate was positively charged, the other was negatively charged. He had a source of matter. This tube was in a vacuum, and with a small sample of matter, he was able to excite the matter, accelerate it, and crash it into the positively charged plate. So we're now going to recreate some calculations to show what Joseph John Thomson did. So Thomson set the magnetic field and the electric field equal. So the magnetic field, or the force because of the magnetic field, EVB, he set equal to EE. So this is the force because of the magnetic field, this is the force because of the electric field. So here, E is the charge on the electron. The cathode ray subsequently was relabeled the electron. V is the velocity of the electron. B is the magnetic field. So EVB is the force because of the magnetic field. E is the charge of the electron, or the cathode ray. E is the electric field. So we set these equal, or Thomson set them equal. F is the force of the electric field. Well, this implies that VB equals E if we just cancel the electric charge from both sides, which you can now see that the velocity of the cathode ray is equal to E over B. So the velocity of the electron is the ratio of the electric field to the magnetic field. Using kinematic equations of motion, so basically equations, we saw kinetic energy, so kinematic equations are just equations that can be used to explain motion, Newtonian motion, classical motion. We're going to look at this deviation here, S. S essentially is the midpoint of the tube, but it's through a distance s that the electron accelerates. S is here labeled in the y-axis, so let S be the change in y as a function of time. Let S be the change in y as a function of time, and if we follow kinematic equations, which I'll state, I'm not going to explain in this video, I'll just state them. The only term that survives is acceleration, change in time squared over 2. So the change in the y-axis, or the distance s, is the acceleration of the cathode ray, the time of travel of the cathode ray squared over the number 2. We're going to solve for delta t squared, so let length, or distance, equal speed times time. So the length traveled, or the length of the tube, or the length traveled, is the velocity of the object over the time of travel. So this means that delta t squared is L squared over V squared. Okay, delta t is L over V, so delta t squared is L over V squared. Newton's second law tells us that force in general is mass times acceleration. So if we sub in acceleration into here, we have acceleration is force over mass. So if I now substitute this acceleration in here, we have S is force over mass over the number 2, and then delta t squared, which is L squared over V squared. There's two things I need to do to change this equation now. I'm going to rewrite F, or the force, as the electric force, which is the electric charge times by the electric field. And I'm also going to substitute in V, where V is the electric field over the magnetic field. So S equals force, but again, force is the electric charge multiplied by the electric field over 2m, and then I have L squared over V squared, but V squared is E squared over B squared. The B wraps back up around. Okay, I have some variables now that will cancel. So I have the electric field here that cancels one of the electric fields here. So let's rewrite that. So E over 2n is L squared B squared over E. And what we're interested in is this charge to mass ratio. Joseph John Thomson contributed the charge to mass ratio of the electron. So let's isolate charge to mass ratio. So the charge to mass ratio, so I need to take the 2 upstairs. So it's 2s. Remember, on the left of the equal sign is s. So it's 2s E, and we take L squared B squared downstairs, L squared B squared. So we have an equation now for the charge to mass ratio of the electron. Joseph John Thomson was able to show this is approximately 1.8 by 10 to the 11 units of Coulomb per kilogram. So the charge of the electron was measured in coulombs, the mass of the electron in kilogram, and this was the major contribution of Joseph John Thomson. In the next video, we'll see how this links in with the contribution of Robert Millikan.